Alrighty, how you guys doing?
No joy.
All right, no joy. Okay, I'm doing pretty well. I wanted to let you know that I have figured out the technological hurdles. I've been able to post the videos online. So if you go to YouTube and you search for Electronics ARC, you should be able to find the videos. I think I've gotten one of them up so far, and I'm in the process of posting the rest. So they should be up probably by the end of the weekend. Yeah, you guys can check those out. If you are sick and you miss a day, or if you just want to review something, feel free to go on there and check it out. So today we're going to talk about Class B and Class AB amplifiers. Okay. We're going to start with a quick review of common collector amplifiers that we saw last time. So we'll talk about the fact that they're current amplifiers, their output is in phase, and we'll look at their Q point, their quiescent point. We'll also go over Darlington Pairs like we saw last time. We'll talk about their gain and the bass emitter drop for those. Then today in lecture, we'll start by talking about Class B amplifiers. We'll see that this is another type of current amplifier. The benefit of a Class B amplifier over a common collector amplifier is that the Class B is much more efficient. You remember the common collector amplifier had its Q point sort of right in the middle of the that graph. So it was using current even when no signal was coming in. We'll see that the Class B amplifier has its Q point way down at the bottom right-hand corner, which means that it does not draw any current at all when there's no signal. So that's a benefit. We'll see that it does suffer from something called crossover distortion. What this means is that when you have very small signals coming in, the amplifier does not amplify them at all. It has something called a deadband right in the middle. So, right where the signal crosses over from positive to negative, you don't get any output. So this is bad. It results in this crossover distortion. So the plus side with the Class B amplifiers is that they are more efficient, but the downside is that they have this crossover distortion. So we'll look at Class AB amplifiers. These are a type of amplifier that try to get the best of both worlds. They want to have the nice reproduction of Class A amplifiers with the higher efficiency of Class B amplifiers. So they're trying to get that efficiency while eliminating that crossover distortion. And we'll see how they do that. And we'll see that the Q point is close to the bottom right-hand corner. It's just a little bit up. So it's using very little current when there's no signal coming in. Okay? So any questions about that before we get started? Yeah?
In practicality, in the real world, are Class B amplifiers used very much, or is it normally a Class AB?
Primarily Class AB, yeah. Other questions? Yeah?
Is the Class B means like a beta? Is it the same or?
No, it's not beta. They're just different classes. So there's a Class A, Class B, Class AB. We'll see a Class C next time. There's actually Class D and other classes as well, but we won't talk about those. We're just going up through Class C in this course. Other questions? Okay. So let's start with a quick review of common collector amplifiers. So we said that the basic form of a common collector amplifier looks like this. We've got our input here. Generally, there's a capacitor. We have these two biasing resistors. This is our supply voltage. That also goes over to a transistor. Now, where did we attach our output for a common collector amplifier?
After emitter?
At the emitter. That's exactly right. So the collector was attached to power, and there's a internal capacitor between the positive side of the power and ground. So AC signals are connected to ground. So we call this a common ground. We call it a common collector amplifier because signals can go from the collector to ground. So this is our basic form of the common collector amplifier. Was this a voltage amplifier or a current amplifier? I'm sorry.
Current amplifier?
Thank you. Yes, it's a current amplifier. And another name for this was the voltage follower amplifier, right? Because the output voltage followed the input. So as the input voltage goes up and the output goes up, and when the input goes down, the output goes down. Another way to see that is that the output, remember that the transistor acts almost like a pair of diodes. So there's almost like a diode between the base and the emitter. And we know that when that's forward biased, there's about a 0.7 volt drop there. So we know that the output is always going to be about 0.7 volts below the input. Often we'll put a capacitor here to remove any DC bias between the emitter and the output. So this blocks DC signals, but it allows AC signals to go through. So, any questions about that?
That is not the swamping capacitor.
Right. This capacitor is between the emitter and the output. This just blocks any DC voltage from the emitter going to the output. Do you guys have a question? Do you have a question? You okay? Yeah.
So the bigger the capacitor on the output side, it's supposed to be the cleaner the signal you get out, right?
Right. Yeah. You would block the DC more effectively, and you would pass the AC more effectively. Yeah. But you run into certain limitations in terms of size eventually. I mean, just if you're trying to build a small circuit, large capacitors get physically big and they start crowding things out.
Doesn't, if you put a bigger capacitor in there, doesn't it start to block low frequency or it reduce low frequency AC also? Or does it not act like a filter?
I believe that a larger capacitor actually passes the low frequencies better. I'll have to double check on that, but I believe that's the case. Other questions? Okay. All right, so that's a little bit about Class B amplifiers. Right. About common collector amplifiers. Thank you. Yeah, right. Jumped ahead a little bit there. A little bit about common collector amplifiers. So let's talk a little bit about Darlington Pairs. So we said that with Darlington Pairs, they're actually a pair of transistors that work together. So you have one transistor here, and then that actually feeds into another transistor. So if this transistor has a gain of 100, and this one has a gain of 100, how much gain does the whole system have? 10,000. Right. The gain of the whole system is the gain of the first transistor times the gain of the second transistor, because any current that goes into the first transistor gets amplified by the first gain and then again by the second gain. So the gain, the total is gain 1 times gain 2. Right? On the downside, there are 2 transistors working together, so that means that there are 2 voltage drops between the base and the emitter. You have one there and one there. So there's a 1.4 volt drop between this terminal and this terminal, as opposed to just a 0.7 volt drop between the base and the emitter on a single transistor. And we said that this pair of transistors acting together has 3 terminals, just like a single transistor, right? So this pair of transistors together acts almost like a super transistor. And in fact, some companies manufacture chips that are called Darlington transistors, which are really just one chip with 2 transistors inside connected like this. They still have a collector, a base, and an emitter on these Darlington transistors, but they're really just 2 transistors hooked together like that. So, any questions about those? Yeah.
Are there any passive components built into the integrated circuit that to limit resistance or to limit current?
I don't
Or
think
anything
so.
like that? It's okay.
No, as far as I know, it's just the
Pure
2 transistors.
transistors.
Yeah. Other questions? Okay, cool. So that's a little bit about Darlington transistors. Darlington pairs. All right. So let's talk a little bit about Class B amplifiers. Okay. So Class B amplifiers use 2 transistors that work together, but they're in a different configuration than the Darlington transistors. So for a Class B amplifier, you have a situation like this. This is your input here. Okay. So you've got your input over here. You've got a capacitor which blocks out DC signals. You've got 2 transistors here. And these 2 transistors, this top one is an NPN, and the bottom one is a PNP. Okay? So so this top transistor gets turned on when the input goes positive, more positive than the output here, and the bottom one gets turned on when the input gets negative. So these transistors actually act together. They act in sort of a push-pull configuration. Okay. So let's take a look at input and output signals and see how this circuit works. So we can imagine an input signal that's like this. It's a small sine wave. When the input goes positive, we get a positive voltage there. And then that sends current through here. The input is positive, so the current does not flow down to the ground, really, through this leg. It mostly flows through this capacitor and flows down through our resistor. Okay? So we see that the input starts to go up, but the current doesn't start to flow until the input is about 0.7 volts higher than the output. So we have this little section where the input does not flow. I'm sorry, where the output current does not flow. So let me draw this a little bit bigger. It's terrible. Okay. So the output is always trying to be about 0.7 volts lower than the input. But when the input is less than 0.7 volts, the output doesn't flow at all. When the input goes negative, then current flows this way. It flows up from the ground. Well, I guess technically it would be flowing in this direction. It would go that way and then down to the ground. But again, it would not start flowing until the output was about 0.7 volts below, or until the input was about 0.7 volts below 0. So we would have this slight deadband there because of this 0.7 volt drop between our base and the emitter. So this is what our signal looks like. Our green is our input. It's this nice smooth sine wave, but then our output has these little chunks near the 0 point where the output does not flow at all. Okay, so this is called crossover distortion because it's distortion that happens right where the signal crosses over between positive and negative. Okay. Do you guys have questions about that? Yeah.
Output also on top or right side.
is the out what? So on top, this is the supply voltage. Yeah.
This is not in, right?
Right. It's not in. So yeah. So yeah, exactly. So when you have a positive voltage on the input, a small amount of current flows through there, and that allows a large amount of current to flow down from the supply voltage and through our load. Similarly, when you have a negative voltage on the input, a small amount of current flows through there, and that allows a large amount of current to flow back this way. Okay? So this is a current amplifier. It's not a voltage amplifier, right? The voltage actually goes down a little bit, but it's a current amplifier. And let's talk about the cue point for this amplifier. So this is the DC load line. Remember, this is the current through the collector, and this is the voltage between the collector and the emitter. And DC load line still looks something like this, but when no current is flowing in, so that would be down here, or when you have no signal, there's no current flowing through the system at all. Okay, so that means that the cue point is right here. Okay, when the system is quiet, there's no current flowing. Okay, so this is the definition of a Class B amplifier. It's an amplifier that has a cue point right at zero current. So this makes it attractive because it is very efficient, right? It's not using any current when you don't have any signal coming in, but of course you have that crossover distortion, which is a negative feature. So questions about the Class B amplifier? Okay, so let's talk about the Class AB amplifier. This is an amplifier that tries to get the best of both worlds. Okay? It tries to have the nice reproduction, the nice fidelity of a Class A amplifier while still having the high efficiency of a Class B amplifier. So a Class AB amplifier is very similar to a Class B. The difference is that we put two diodes in between these two terminals. And then we use two capacitors here. Okay. So the amplifier functions in mostly the same way as the Class B amplifier, but these two diodes mean that there's a 1.4 volt offset between the base of the NPN and the base of the PNP. So that means that these transistors are right on the edge of conducting all the time, right? Any small amount of input voltage change causes these transistors to conduct. So whereas the Class B amplifier required a 0.7 volt offset in order to conduct, the Class AB amplifier doesn't require that at all. Okay. So the Q point for the Class AB is just like that, okay? So it's not quite as low as the Class B, it's just a little bit higher. Okay? So it's still pretty efficient, but it's not quite as efficient. There might be just a little bit of current that is flowing even when there's no signal coming in, but it's a very small amount. It's not anywhere near the middle of the line. So, any questions about that? Okay, so that's really all I wanted to say about Class AB amplifiers. For homework, please check out the basic BJT quiz on Canvas. And that's pretty much it. I will take attendance and then I'll let you guys go. I know that last week's lab was a little bit longer. I'm hoping that this week's lab will go a little bit faster, and maybe you guys will have a chance to catch up on if you were a little bit behind last week.